In previous part of the deletion in B tree, I explained algorithm for deletion. Now, just I will explain this deletion of the keys in B tree through example. Okay, so I have already drawn this B tree with degree, minimum degree t equal to 3. So the minimum number of keys in any node is 2 and the maximum number of keys is 2t minus 1, that is 5. Okay, as I told in the deletion case, we whenever we move from root to the leaf node, in the path every node must contain t number of keys, one more than the minimum number of keys, and this condition doesn't hold for the root. Root can contain at least one key. Suppose this is the case, there is a difference between the insertion and deletion. In the case of insertion, we move from, for every insertion we start from the root. At any particular time if the root is full, so first we have to delete the root. Here the root may contain the one key. Okay, so simply it is the number of keys in every node is t. This is not applied to root. So in case of deletion, when we delete any key from the B tree, then we move from root to the leaf, and in that path all the nodes other than root must contain t number of keys. So now just I have drawn this tree with degree t equal to 3. So simply just I will start from the root node. Okay, this the algorithm will start from the root node, and the first key what I want to delete is 12. So here the k is 12. The key to be deleted from this tree is 12. So here x is pointer to the root node. I said that root node can contain at least one key. So here the condition is satisfied. For the root is not required to contain the t number of keys at any particular time, as the tree may contain the single key. So in that case the binary tree B tree contain, the root node contains single key. So here x is pointing to the root node. So 12 is not present in x is root, so it is internal, it is not leaf. So and check it, 12 is present in x or not. 12 is not present in x, so it will go into the second case. Second case is that when the key is not present in the internal node. So here it is not present in the internal node, so it will find the root of the appropriate subtree in which the 12 may be present. So here the 12 is less than 50, so the appropriate root of the subtree is this one, that is C1x. Here I have written in the algorithm Cix. Here the value of I is 1. So simply the if the 12 is present in the tree, then it must be present in the subtree rooted at C1x. But before calling the recursion through C1x, we have to check that number of keys in C1x, because C1x is C1x for the deletion. Every node other than root in the path from root to leaf must contain t number of keys. So here this node contains t number of keys. Here the t is what? 3 number of keys. So now the problem is converted to recursively delete 12 from the tree, from the subtree rooted at C1x. So in the next recursive call, this will become what? X. Okay. So again the deletion procedure is called. Now at this time x is pointing to this node. Okay. So again the first case was that key x is leaf and k is present. So x is not leaf. Okay. Now the 12, it will check 12 is present in k x or not. 12 is not present. X is internal node and 12 is not present. So it will go to the second case. Now simply the 12 is not present, so it will find what? The root of appropriate subtree in which the 12 can be may be present. So here the appropriate subtree of x is C2x. Now again before recursively deleting the 12 from this node, first check whether this node contain t keys or not. So this node contain t keys. So now the problem is converted to delete k from C to X recursively. So in the next time the deletion procedure will become this will become X. Okay, now the delete procedure is called and this will become X. Now it will go to the first case when X is pointing to a node and X is a leaf node and K is present in the leaf node. So simply just shifting off, because this is leaf node, so simply we shift one location left all the elements and 12 to be deleted. So here the safely we delete 12. You have to draw the separate B tree. Here in the case I am just overwriting in the same B tree. So simply just all the keys deletion I have taken one by one. So simply you on the paper you draw the tree and then here you write K equal to 12 and after deletion this is the resultant tree, and now in the resultant tree I will consider the second key to be deleted. So after deleting 12, this is the resultant tree. Okay, now the next key I will, this is the resultant key, this is the resultant tree after deleting 12. Now the next key what to be deleted is 20 in this. Okay, so again every deletion, suppose here I am taking the every deletion, I will start from what? X, because the deletion procedure is written to delete one element at a time. So X is pointing to the root, so it is not required that X contains what? T number of keys. So X contains. Now find the appropriate child. So here the appropriate root of the subtree in which the 20 may be present. So here this is C1X. Okay. C1X. Now check it. C1X, before calling recursion again, C1X contain T number of keys or not? Yes, C1X contain T number of keys. So simply and the 20 is present in this key, so it will go to the what? Before calling the T number of keys, so now the recursively delete the 20 from the subtree rooted at this C1X. So in the next time in the recursion this will become X. Okay, now here the X is not leaf, so first case is not. Now the 20 key to be deleted is present in the node pointed by X, so it will go to the third case where the K is present in the internal node. Now just that is, again there are three cases. In the case of third case there are three cases. The one is if the child y that precedes 20, this is the child that precedes 20 and this is the child that follows 20. If the child y that precedes 20 contain t keys, this is not the case because it contains only 2 t keys and t is 3. Okay, so just we have to check X, what the tree Z that follows 20 and it contains t number of keys. So what we do, this is the second case and third B case. This is the third B case where the tree that follows 20. So in that case K is 20. So we have to find immediate successor of 20 in the subtree rooted at Z. Here there is only one leaf node, but there may be the number of level. It may be the case that there is a lot level and here somewhere here we get what? K dash. So suppose the height of the tree is more. So in that case the immediate successor of 20 is K dash. So what we do, just simply our objective, our aim is to delete the immediate successor K dash that I will get in the subtree rooted at Z, the leftmost child, the first key of the leftmost child, that is leaf. Okay, so here this is the leaf, so 22. So our problem is to delete the immediate successor of 20, that is K dash k dash to be deleted in the subtree rooted at z, and this should be done in the single pass by taking the either going to the first case or second case. If it contains not t keys, then merging of the keys will be involved. Okay, so here this contains, so this is what immediate successor. So this is what k dash. So what we do, just we have to simply replace the recursive. We delete what? We replace k by k dash. So here 20 is replaced by what? 22, and now the problem is converted to delete k dash in the subtree rooted at z. So this will, again the recursion will be called, and this will become what? X, and then it will go to the case 1, as x is what? The leaf node, and 22 is present in the leaf node. So here the 22 is deleted. Okay, so simply just after the deletion of 20, this is the resultant B tree. Okay, now you draw the separate diagram. So after deleting 12 and 20 in the original B tree, this is the resultant B tree. Now the next key is 25. Okay, again I will start from root. Okay, so this is x. Okay, so now just we find the appropriate child 25. Appropriate child 25 is this one, C1x. This is the appropriate child. Now C1x contain t. So C1x contains what? T number of keys. So recursively delete 25 in the subtree rooted at C1x if the 25 is present. So simply now the recursion will be called, again the recursive procedure is called by making this node as x. Okay. Now this will not go to the first case as x is not leaf. Now the second is 25. So here this is not the third case. So this is the second case. Second case means the what? K to be deleted is not present in the internal node. Here x is internal node and 25 is not present in x. So simply what is the case? That if it is not present, then we check what? We find the appropriate root of the appropriate subtree. So root of the appropriate subtree k equal to 25 is this one, C3x. This is the root of the appropriate subtree in which the 25 may be present. If the 25 present in the tree at all. Now just here, just there are again three cases. That first what we check, its immediate left sibling. If its immediate left sibling contain the t number of keys, then simply just we perform the rotation, but immediate left sibling doesn't contain t number of keys. Now check its immediate right sibling. This is what? The second B case. The immediate right sibling. Immediate right sibling here, what? Immediate right sibling contain the t keys. So what we do here, this is what? Z. So what we do, just here we perform this type of rotation, C3x, this is C3x, this is rotation. Okay, so what is that rotation? The 40 is moved, 30 is moved down to C3x. Okay, so here make the room for that. 25, 28 and 30. 30 move down to the down to C3x, and the first key of Z move up to the x, and this will become what? The ith key of x. So here this is 40. Okay, and the next is, if suppose this is not leaf, then the child of what? 40 will become the child of 20, and this is a leaf node, so this is not required. Okay, so now after now I will finally just now, so what happened, this 40 will be deleted from here, and if suppose this is a leaf node, if this is not leaf node, then the first child of Z will move to the last child of C3x. So here there is a 40. Okay, now in this way what I did, simply C3x contain now t number of keys. Means our target is that whenever we are moving from root to the leaf for deletion, in the path, if any node other than root not containing the t number of keys, so first we have to make this sure that this node contain t number of keys by performing either merging or by rotation. Okay, so now this is what, so now the recursively delete, the process is converted to delete the 25 from this node. So again the recursive procedure is called, and this it will become what, x. Okay, the control is transferred, the recursive function is called only when that sure that the CIX contain t number of keys. So now the problem is converted to delete k, that is 25, in the subtree rooted at C1x. So in the next recursive call this will become x. So this is what, finally this is what converted into the first case. Always recursion terminate at the first case. X is pointing to the node and this is the leaf node. So 25 is deleted. So here safely the 25 is deleted. Now the 25 is deleted and this is the resultant tree after deletion of 25. Now next is what, k equal to 60. You draw the separate tree, k equal to 60. So when we delete k equal to 60, so again we start from the root node. Now when we start from the root node, so simply the root node there is no condition of t keys, it can contain at least one key. Now find the appropriate child. So appropriate child where the 60 may be present, this is C2x. Okay, C2x. So before moving, I have to check the C2x contain t keys or not. C2x doesn't contain t keys. So simply what we check its immediate left sibling or right sibling. So here, so simply just its immediate left sibling is this one. So immediate left sibling is this, and the right sibling doesn't exist because this is the rightmost node. So simply just it contain what, t number of keys. So we perform this type of rotation. This is the case. This is the second case. As the 60 is not present in the internal node, so it will find the root of the appropriate subtree in which the 60 may be present. And before recursively delete, we have to make one key more in this node. So I will find its immediate sibling, that is y. So what we do? Just simply the 50 move down to the C2x. So here 50 move down to this one. Okay, and then the last key of y will move up to the x, that is 40. Here this is 40, and the last child of 40, here this will be the child of 50. Okay, now see, this is the case. And now from this node y, the 40 and this is to be deleted. Okay, and here this is 40. And now the because now the C2x, the node pointed by C2x contains t number of keys, so the problem is converted recursively delete 60 from the subtree rooted at C2x. So the next time this C will become, in the next recursive call, this will become x. Okay, now this is the subtree after rotation. Okay, now k is what, 60. Here the k to be deleted is 60. So here 60 is present in x. So this is the third case when the key to be deleted is present in the internal node x. So in that case what we do, simply just we check. The first is we check its immediate left. Immediate left is y. Contain t keys? No. The child that the immediate followed, and that is z. So here the child z that follows 60 contain t number of keys. So what we do here, we find the immediate successor of 60 by moving in the leftmost subtree, and this will be performed. So here the immediate k equal to 60, so immediate successor k dash, immediate successor of 60 is what? 62. Now the 62 k will be replaced by this k dash 62, because as our aim is to delete 60, so we cannot delete directly. So what we do, just either we check it's the subtree that precedes 60 or the child that follows 60. So here the child that precedes 60 doesn't contain the t number of keys, so we go for this. Now the problem is converted. Just simply the problem is to delete the k dash, that is 62, from the subtree rooted at z. As this is a leaf node, so simply the simple case, it will be deleted by shifting it to this, and the 62 is deleted from the leaf node. So now after deletion from 60, this is the tree. Okay. Now the next is, so 60, and now the next is 62. Suppose the next deletion is k equal to 62. So when we are deleting k equal to 62, so again it will start from what? Root. It will start from root. Now this is the appropriate child, that is C2x. It contains t number of keys. Now the recursively delete 62 from the subtree rooted at C2x. So this will become x. This will become x. Okay. Now the again the recursive procedure is called. Now this is converted in the case third. The key to be deleted, k equal to 62. The key to be deleted present in the internal node. So again here what the y is this one, y, the child that precedes 62 and the child that follows 62. So here the y doesn't contain t keys, and z also not contain. So this will go to the third, this is the what? Third A, third B, third C. This is the third C case, in when neither the child that precedes 62 and the child that follows 62 contain t number of keys. Then what we do? Just we perform merging. The merging, what? We merge all of the z and the k into y, and z is to be deleted and the x loses the key 62 and the pointer to z. What actually I did in the case of insertion, when I split a node, then z is to be created, one new pointer is created, and middle key is moved up. So just the reverse of this is to be performed in the case of merging. Here all the keys of z move to what? Y, and this key will become the tth or median key of this. So simply here this is what, and this is 62, and this node x loses this pointer to the z, and now of course the z is to be freed or deleted. Z memory is allocated through new, and here this is now. So simply this is the deletion, and now in this way now the problem is converted is to delete what? Find the appropriate where the 62 is present. Now the problem is converted to delete 62 from this merged node. So here now the recursively will delete 62 from the tree pointed by x. Now this is a recursion every time you see. So now this is converted into what? The first case. The x is a leaf node, and the key to be deleted is present in the leaf node, and finally it is deleted by shifting the keys. So here this will become 65, this will become 68. Okay. So here this is what after deletion of 62, this is the tree. Now the next is k equal to 65. Now k equal to 65. I have to delete the 65 keys in 65, the k 65 in this. Now simply this is x. Okay, as it is pointing to the root node. So root node, there is no restriction that root node contain t number of keys. Find appropriate subtree where the root of the appropriate subtree in which 65 may be present. So this is what? C2x. Now here the first, before calling the recursion, we make sure that the C2x contain t number of keys. Here C2x doesn't contain t number of keys, it contain only what, t minus 1 keys. So check it what, so this simply, this is the actually this is the case what, the second case. Second case, when the 65 is not present in the internal node, so it will find the root of the appropriate subtree in which 65 may be present. So now just here this C2x, the node pointed by C2x is not containing what, the t keys, so then immediate the right or left sibling is to be checked. So here the right sibling doesn't exist, simply see here this is the case, that immediate left sibling also contain t minus 1 keys. So it is not contain, if it contain t minus 1 keys, then I will do the rotation, but here it doesn't contain what, t keys. So what we do, we perform merging, and this is the case when the height of the tree is reduced by 1. Okay, so simply again this is y, the child, and simply just we merge all the z into y and then 40. So here this is 40, see this is the case. (22), 40, and now just the root node, the left child, that wise, of course this pointer is deleted and this node is deleted, freed, and what, the this node also to be deleted, and this will become the new root of the tree. Here this will become the root of the tree. In this way the height of the tree is reduced by 1, as the height of the tree is increased in the case of insertion when the root is full and it is splitted. Here in the case of the deletion, when both the child of root contain t minus 1 keys, then before moving down we have to merge these two nodes, and then finally the problem is converted to delete what, the 65. So when we delete 65, so again the recursion will get, so it will go to the what, second case, 65 is not present in this, so find the appropriate subtree. So C1, C2, C3, C4, C1, C2, C3, C4, C5. So appropriate root of the subtree where the 65 may be present. So C2, C5x contain t number of keys, in fact more than t number of keys. So here just the recursively delete 65 from this course, this case, so this will become what, x, and now the this will be converted into the first case, x is a leaf node and 65 present in this node, so this will become 68 and 65 is deleted. Okay, so this is 65, and now the last is when I will delete 50. So this is what, x, this is x, and it will go to the third case where the x is what, present in the internal node. When the x is present in the internal node, then the child that precedes, that is y, that precedes 50, and the child that does not contain t key, so child that follows 50, so simply here that is what the contains, so simply what, the immediate successor of 50, k dash is 53. So simply replace k by immediate successor, which we will get in the leftmost subtree of the subtree rooted at z. So 50 is replaced by 53. Now the problem is converted to delete 53 in the subtree rooted at z. So this will become x, and now the problem is to delete k dash from the subtree rooted at x. So here the 53, so this is converted into the first case, x is a pointer to the node and it is a leaf node, and the key is present in this node, so this is deleted. So here this is the case. Okay, So I have covered all the cases, first, second, third, with the help of this example, but I have it is not possible for me to draw the separate B tree again and again, but carefully you draw the, after every deletion you draw the new tree. Okay, so 1 2 3 4 5. Suppose in the same if I want to insert one key, if I want to insert one key, say suppose just here after deletion, suppose in the tree I want to insert k equal to 72. Again I am saying insertion. If I want to insert 72, then we start from the root, and here the root is full. So but first root is splitted. So root is splitted. So simply just this will move up, and this is this one, and here just this, and this will become the right child. Okay, now the insertion is simply to delete. For insertion, this node is not full, so here the recursively delete 72 from 72 from inserting 72 from in the node X. Now as the 72, so simply just we have to find the appropriate child, because the insertion always performed in the leaf. So 72 can be inserted here, so we move this child, and simply the 72 will be inserted here, 72. So in this way you can perform insertion also by splitting the key and from root to leaf. Again I am saying, remember that in the case of insertion, insertion is performed at the leaf node. So when you move from root to leaf in the path, if any particular time the node is full, then we have to split the node before moving down. We did show that it contained the one place for the key that may be coming from its child in the splitting process. The second is in the case of deletion. So in the case of insertion, this condition is applied to the root also. It will start from the root. If the root is full, then first root is splitted. But in the case of deletion, this again, the way the deletion is more complicated in the sense that key may be present on the internal node, as well as the key may be present in the leaf node. So this is more complicated, and the rule is opposite. Here when we delete and we start from root to the leaf, so in the intermediate, if any node contain the t minus 1 keys, so first we have to make t keys. So in the path from root to the leaf, other than root must contain t number of keys. Okay, so this is all about the insertion and deletion. Now I will tell you the height of the tree. As simply, just I told earlier that the degree of the B tree, can be very large. Degree of tree decide the branching factor, and because this B tree is designed for secondary storage device where the bulk of data is stored, so the degree of tree can be equal to the one size of the one sector of the hard disk or one page or block. Actually the degree of the tree depend on the basic unit of the secondary storage device. So here I am giving the what is the worst case height to store n number of keys. Okay, so the worst case height means key in the case, because here our target is to reduce the access time. If the height is less, then the access time will be less. So that's why here there is a concept that all the leaf node are at the same level. So, okay, so what is the height, worst case height in a B tree with n keys, where n is greater than or equal to 1 number of keys, and minimum degree n keys and minimum degree t greater than or equal to 2. The height of a B tree, height of a B tree with n keys n is greater than or equal to 1 and minimum degree t greater than or equal to 2 is h is always less than or equal to log t n plus 1 by 2. Okay, so to store n keys, this is simply the worst case height. The height will always be less than or equal to this. Okay, so simply here this is the worst case height. So now I will show ki when will be the worst case height to store the n keys. To store n keys, the height will be, just say for example, what is the meaning of this, that suppose here we are considering we are taking the example of binary tree. So in a binary tree, if suppose we are storing the 3 keys, so simply this one and this one, so height is only 1. But if the same we store what in this way, so height is 2. So our objective in this calculations is I want that the maximum height to store what n, the worst case height of the B tree in what B tree to store n number of keys. This is when the every node store minimum number of keys. Minimum number of keys, here in the case of binary tree there is a single key, or we can say that the minimum number of children. The branching factor I will take minimum. Okay, so just if I want to prove this, that h is less than or equal to, so here see I will start from the root node. Okay, I will start from root node. Okay, so every node, our objective is to store the n number of keys with maximum height, and this is possible when every node contain the minimum number of keys. Okay, so because we are considering the worst case height to store n keys, so in the case of root, the minimum number of keys. So here I am writing what the level, or you can say that the height, and the number of see, this is the root node, and here I am writing what the level and number of nodes. Okay, so this is level, or you can say that the height. So at the level height, you can say that this is height also. Here I am taking the height as 0. Here the height is 0, then the number of node is 1. Okay, now we are storing minimum key, so minimum key in root can be 1. The minimum number of keys in the root must be 1, the lower bound. Okay, so now here there are, because there is a single key, so there are 2 nodes at level what 2. At level 2 there are what level 1, sorry, this is the level 1. Level 1, how many number of nodes? 2 number of nodes. Okay, because both the nodes, this node contain the minimum number of keys. So here the minimum number of minimum number of keys are what? T minus 1. So minimum number of children, this is what? T. Here also the minimum number of children, this is what? T. Okay, so here in this case what? At height 2, at height level 0 and level 1, this is 1 and this is 2. So this is what height is 2. Height is 2. So simply see, there are what the t number of nodes. Here I am writing number of nodes, not number of keys. Number of nodes at each height. Number of nodes here t. So simply it will become what? 2t. Okay. Now here there are t keys, and every node contain what? T number of nodes. Okay. Again this will contain what? T number of keys. this will contain t number of nodes and this will contain t number of nodes. So at height 3, at the height 3, there are what? Simply what? 2t number of nodes, and every node contain what? T number of children. So t number of nodes. So at height 3, so if we take this one, at height 3, this what? The same is here. This is in this way. So at height 3, 2t into t, that is 2t square, and so on. Okay. So at height h, this is what? 1, first height पे 2 है, second height पे 2t है, थर्ड हाइट पे 2t स्क्वायर है. सो इन दिस वे फोर्थ हाइट पे 2t क्यूब हो जाएगा. h हाइट पे 2t h minus 1. Okay, and now the simply suppose the height of the tree is h. So I will add all these. So the number of keys, minimum number of keys, the keys can be more in the height h key, because here I have considered the minimum number of keys. Okay, so simply just here the number of keys n greater than or equal to just the number of nodes multiplied with what? T minus 1. Here this is what? So 1 plus 2 plus 2t plus so on plus what? 2th minus 1. This is what? The number of here. From you start from here, just, or you can start here also. The n is greater than or equal to, here this 2 plus 2t plus 2t square plus so on plus 2th minus 1. Here the 2 number of nodes, so 2 multiplied by t minus 1. T minus 1 number of keys. I am talking about the number of keys. So this multiplied with t minus 1 plus 1, as the root node contains single key. Other than root node, all the nodes will contain what? T minus 1 keys. So 2 into t minus 1 number of keys at level 1. 2t into t minus 1 number of keys at level 2, and so on. So this is the formula. So here n is greater than or equal to, take 2 is thus 1 plus t square plus so on plus t h minus 1 t minus 1, and right here this plus 1. Okay, now this is a geometric series. So n is greater than or equal to 2, just t is the geometric ratio. So t ki power, there are total term h minus 1 here. This is h minus 1. So simply the t ki power h, as these are the h term, minus 1 upon t minus 1 into t minus 1 plus 1. This is cancelled. N is greater than or equal to 2 t to the power h minus 2 plus 1. So this is n is greater than or equal to 2t ki power h minus 1. So here we can write 2t ki power h is less than or equal to n plus 1, and then t ki power h is less than or equal to n plus 1 by 2. This implies that h is less than or equal to log base t n plus 1 by 2. Okay, so now see, if the height of the tree is less than or equal to what? What is the meaning of this? See what it is saying, that the height of the tree is less than or equal to log t n plus 1 by 2. This I have calculated the height when the every node in the B tree of minimum degree t contain the minimum number of keys. Okay, so what is the meaning? That suppose here I am taking like n equal to say the n equal to is 1,99,999 1,999. Okay, so 1,99,999. This is n. Okay, so if we consider this n, then we add n plus 1. So n plus 1, that is n plus, this is n. Okay, so n plus 1, n plus 1 will become 2 lakh. Just we add it. So 1,99,909. So simply it will become what? 2 lakh. Okay. Now this n plus 1 divided by 2. N plus 1 divided by 2, it will become what? 1 lakh. Okay. And now simply if I will consider, so n plus 1 by 2 is equal to 10 to the power 5. Okay. Now suppose I am taking degree of tree is t as 10. If I will take degree t as 10, so log 10 to the power 5 is what? 5. So what? Height is less than or equal to 5. What is the meaning of that? This that if I will take the minimum degree of the tree is 10. So the in a height of less than or equal to 5, the minimum keys what I can store is what? Approx 1,99,999. This is the minimum number of keys in the height 5. Now if you go to the maximum number of keys, then you have to take the 2t number of keys, 2t minus 1 keys in the height 5. Okay, so just how you can see that if the degree of the tree is equal to the one sector like 2 to the power 10 or 2 to the power say 5 or 2 to the power 8, then just the number of keys will be stored in the B tree of very few height. Okay, so now this is all about B tree. And now again, if suppose you are you want to perform the any function, like say suppose you have to search. You have to search now the any like searching and to find the maximum element in the B tree, find the minimum element in the B tree, or any type of, I have discussed only the insertion deletion, but now you know the structure of the B tree. Suppose you want to search, there is a function to search a given element in the B tree, and recursively I will write the search function. So when you are going to write the search function, so simply what the search function? Search function will take what? X, the pointer to the node, and the k to be searched. K is the key. So you will take I equal to 1 because the element may be present in the internal node or element in the present in the subtree. Okay, so first we will find whether the k is present in what subtree or in the leaf node, sorry, or in the node. So what we do, while I is less than or equal to nx, the loop will run to the number of keys currently stored, and key of I x is less than k. Okay, now this is the case. Suppose in the B tree, here suppose x is pointing to the node like 10, 20, 30. 10, 20, 30, and our objective is to find the 30. Okay, so here the 30, so suppose I is equal to 1, I key I, so 10 is, k is here 30, k is 30. So simply the k ix, 10 is less than 20 is less than 30 is less than 30. So here it will stop, I will be incremented by 1. So if suppose if the key is present in the node, then it will come out in between. So here you check if I is less than or equal to nx, and here I have not checked the equality condition. So key I x equal to k, then simply return the x, the pointer to the node in which it is present, and at what position, that is I. It will be present in the ith position. Okay, if this is not the case, so simply if if leaf of x, and this condition is false, the return not, so and x is leaf, So of course return what? Nil, element is not present. Okay? And if x is not leaf, if x is not leaf, suppose here some 25 you want to search, 25. So 25 will be present in the subtree rooted at what? Just here the 25. So it's just the pointer to be written what? The I is 10. 10 is less than 25, I plus plus, 20 is less than 25, 30. So it will return I is here 2, and this is also correct 1, I will return 3. So 3, so ith child will be read from the else disk read the root of the subtree in which the 25 may be present, disk read what? Disk read C I X, okay, ith child, root of the subtree in which the 25 may be present, and then again you call this function search CIX. Now the problem is converted to search the key in the subtree rooted at CIX k. Okay. So this is the search function. In this way you can write any function. Suppose our objective is to find the minimum key in the B tree. So where is minimum key? The minimum key in the B tree is the first and then the last child will be the minimum key. Maximum key in the B tree, just you go to the rightmost child for every node until you get the leaf node, and in the leaf node the last key will be the maximum key in the B tree. So now you try to write any function given with the help of this idea of B tree. Always remember the structure of the B tree, and you are able to write any function or any operation, algorithm of any operation in B tree. Okay, thank you.